For our first physics experiment for the year, I decided to go with the second option. This is the one where we took a launcher gun, just like this one, and shot it from two separate angles. The first angle is at 0 degrees, and the other angle is at 45 degrees, and see how the two different measurements compare. With this launcher gun, all you have to do is simply pull back a spring, and then launch the bullet. For part 1 and 2 of the experiment, what I did was launch the bullet 3 times and calculate the average. So for example, if I launched it from 45-degree angles, a 45-degree angle, and got 1 meter of height for the first try, 2 meters of height for the second try, and 3 meters of height for the third try, I would average with 2 meters of height, and this would eliminate any potential disruptions to my data. Now for our first part, I decided to start with launching it at a 0 degree angle, roughly 1/3 of a meter off the ground, and see how far the bullet would go before hitting the ground due to the acceleration of gravity. Degree angle from roughly a meter high, I did it right in front of a fence. That way I knew each fence floor or each fence board is about 4 inches, and I can convert that into meters to figure out my displacement and velocity. And I could do the velocity because I took a bunch of photos as the bullet was going through the air, and I can figure out the time in between each photo taken and how much or how far or how many boards this dart has crossed. So to begin with that, I then can do some more math to figure out some distance and compare that with my measured distances to see how close I was. So I knew that I would look something like this, where I launched it from 1 meter up, and then as I measured how far my dart went, I found that it went an average of 3 meters throughout the 3 tries I did this. So because of that, because we know it's going to be a meter in height, we can figure out how much time the dart has in the air before hitting the ground, because that's really the only thing that's going to stop the dart from moving. The air isn't going to stop it. Even though there is some air resistance, it's going to stay in motion until it hits the ground. So because of that, we can figure out the time it takes for the dart to fall 1 meter by using this equation. In other words, the square root of 2 over gravity, or 9.8, will equal 0.45 seconds. So it's going to take 0.45 seconds to fall that full meter. We could determine through the video that the velocity of the dart is 5 meters per second. So we could figure out how far the range is on the x-axis by taking 5 and multiplying it by our time, 0.45 seconds, to get 2.25 meters, or 2¼ meters. So pretty close to that 3 meters, but not really. My theory is because of air resistance of the bullet falling, that gravity is actually going to be, or acceleration due to gravity is going to be a lot lower. This is assuming we were in a vacuum, but that 9.8 may be a lower number, thus giving it more time to be in the air before hitting the ground and having a longer range because of that. So for the next part of the experiment, I got to a lower part of the ground and I used my house as the background. That way I could figure out the height. I could determine the height through the video as well as the range. So here I am launching it from a 45-degree angle. And we knew that it's going to look more like a full parabola, unlike the half of parabola in the last one. So we're launching it, and I could determine through the velocity, which is going to be similar to the last one, because there's not a lot of resistance to gravity with the dart being so light. So we can assume that the velocity is going to be 5 meters per second. So with using this equation to find the range, or how long this dart traveled across, we could figure out that 5 times the sine of 2 times our angle, 45 degrees, over gravity, 9.8, is going to equal around 2½ meters, which isn't the most accurate to what we found. We found it went a little bit further, so I'd like to figure that out more, but we could still use it for the sake. And also figure out how high our dart went. We could use this equation, or we could think about a velocity as a vector, because it is. So if this middle line is the trajectory of the dart, at least for the first moment, before gravity starts to act and it starts to curve, we know that the range is going to be 2½ meters, and we can assume that the height is also going to be pretty close to 2½ meters. which we found that to be pretty accurate looking at the balcony and how high the dart can go up and upwise on the y-axis. So from that, we could figure out the force, which we could determine because the dart is roughly 10 grams or 0.01 kilograms. The force in newtons on the dart from the spring is going to be 0.05. Now, to quickly wrap up our experiment and figure out how much kinetic energy is in that in this dart or in that experiment, we can multiply half of the weight of the dart, which is going to be 0.0. Well, basically, it's going to be 5 grams or 0.05 kilograms times 5 to get 0.025 joules of energy. So with that, yeah, there were a few flaws, a few errors with our experiment, but it was still interesting to see how close we can get to the math to our actual real world. Thank you.